Hello everyone, I am Anup Patel from Ventana Microsystems. Uh, this talk is about RISC-V nested virtualization or in general nested virtualization in RISC-V world. So this talk is divided into three parts. First, we'll start with a short overview of the H extension specification, which was ratified last year in December 2021. And then we'll move on to in-depth details about RISC-V nested virtualization. And lastly, we'll look at the software status and have a short demo about it. So let's start with a quick overview of RISC-V H extension. So the RISC-V extension is well designed and it's suited for both type 1 as well as type 2 hypervisor. It essentially makes the existing traditional S mode into an HS mode, which is nothing but S mode plus hypervisor capabilities. And these hypervisor capabilities are in the form of new instructions like HFENS, GVMA, VVMA, and then HLV, HSV instructions. And then we have CSRs like HCSRs and VSCSRs. So apart from this HS mode, we have two additional modes as well, which is VS mode and VU mode, which are used for running the guest. So guest kernel will typically run in VS mode and guest user space will run in VU mode. So and in HS mode, the SCSRs or the S mode, typical S mode CSR will point to the host context or regular host CSRs. S mode CSR, and in VS mode, the same S CSRs will point to the VS CSRs, and even the SFENS VMA will be an alias of the SFENS VVMA instructions actually. And the figure over here actually shows the different privilege levels with H extension. As we can see, there are 4 privilege levels now. And in addition, this figure also shows that there is two distinct worlds. One is the host world and the guest world, and the hypervisor runs in the guest world, whereas the VM runs in the guest world, right? So for H extension CSR, like I said, we have two types of CSRs. One set of CSRs is prefixed by H letter, and other set of CSR prefixed by VS letter. So H CSRs or H prefix CSRs kind of add the hypervisor capabilities to the and the VS CSRs allow hypervisor to access the guest or VM state basically. And within the HCSR, there are different types of CSR like trap handling CSR, hypervisor configuration CSR, then the page table translation CSRs, and so on and so forth, right? So just like any major artists, we do have a two-stage MMU with H extension. So the host world only uses a single stage, which means that hypervisor itself will need to do a host VA to host PA translation. So there is that is just a single stage called S stage. And then for the guest world, we have a two-stage translation where the first stage, which is converting guest VA to guest PA, is done by the page table SATP program by the guest OS, and then the second stage, which translates guest PA to host PA, is done by the hypervisor. So that is the G stage actually, and this is pretty similar to major artists like ARM and x86. So entry to guest is very straightforward with authorization. So hypervisor will typically do a SRET instruction with SPV bit set in the H status CSR. So whenever this bit is set and SRET is executed, the hypervisor automatically enter in the guest mode and will start running VS or VU mode code or guest code, right? So, and whenever the guest is running and we get a trap or IRQ or SBI call, which was meant to be handled in the HS mode, the VM will or M mode, it will exit and the code path will come back to the hypervisor. So injecting virtual interrupts is also very straightforward. So whenever a hypervisor enters a guest when it enters, if the ending of VSIP and VSI CSR is not 0, then guest will immediately take an interrupt whenever it can actually. And setting the bits in VSIP is also very straightforward. Hypervisor can simply write bits in the HVIP CSR, or we can have an external interrupt control which is capable of injecting virtual interrupts to the VM. So either way, the bits in the VSIP can be set. So now this was a quick overview about the H extension in general, and now we'll look at in depth the nested virtualization in RISC-V world. So before we proceed, actually, what is actually nested virtualization? So nested virtualization is really an ability to run virtual machines inside another virtual machine, right? So, and in other words, like for RISC-V nested virtualization, it means that hypervisor will emulate H extension for the VM. right? So, or guest. And there are various use cases for the nested virtualization. Like primarily right now, it's for software development. Like people can develop mobile applications for Android running inside another VM, and developers can do software quality assurance or stress testing on cloud and all, for that's Android and Android applications, or even the stress testing of cloud management software as well. And this is also useful in sales and education, where you don't need a physical machine to demo or something. You can just take a cloud instance and create and demo cloud infrastructure software inside another VM, right? So yeah, and more future and more in future, more and more use cases will show up actually. So this is like a logical view of how a nested virtualization looks like in RISC-V world. As we can see, compared to a normal virtualization, we have now three worlds. One is the host world, which we also call it L0. Then we have a guest world, which is L1, and then we have a nested world actually, which is L2 actually. And apart from that, you will also see that actually there are special modes highlighted in red, which are like synthetic modes, which don't really exist in hardware, but they are synthetic modes emulated by the host hypervisor, right? So, and the host hypervisor can do this by multiplexing the existing hardware VS and VU modes. So now this is the temporal view of the same nested virtualization which was there in the previous figure, right? But in a more temporal sense, right? So as we can see over here, every vCPU has a nested virtualization state which can be either on or off. So if the nested virtualization state of a vCPU is off, it means that it is running guest world. It is in the guest world actually. And if the nested virtualized state of a vCPU is on, it means that it is in a nested world, right? So running at L2 level, right? And so this figure exactly shows these things. And host hypervisor will also implement a special world switch called nested switch. So apart from a regular context switch, which is switching one vCPU to other vCPU, for a particular vCPU as well, there will be a nested switch. Okay. So in this nested switch is used to change the nested virtualization state from on to off or off to on actually. And like I said, the H extension will be trap and emulated by the host hypervisor. But the thing is that host hypervisor will only emulate H extension for the guest world, which means it will only emulate H extension functionality for the L1 over here or the guest world. So again, for compared to normal virtualization, we now have a 3-stage MMU. Okay, so host world and guest world are exactly same like they used to exist previously in a normal, but the nested world has a 3-stage MMU. Which means that the nested world itself, the kernel running inside the nested world, will do a nested VA to nested PA translation. It will program page table for that. And then there'll be a page table program by the guest hypervisor or the L1 hypervisor to translate nested PA to guest PA. And similarly, host hypervisor will also have a translation of guest PA to host PA. But the hardware will only have 2 stages because that's what H extension defines. So to achieve these 3 stages, we actually have something called a shadow page table programmed by the host hypervisor. So there'll be there'll be a page table in every hypervisor, which is common to the VM for the guest world. And there'll be for every vCPU of a VM, there will be a separate shadow L0 shadow page table. So whenever a vCPU enters nested mode, it will start using the shadow page table. And shadow page table is essentially translating nested PA directly to host PA, and it can do this thing by doing software walks of the G stage page table created by the guest hypervisor actually. So and nested entry and exit, which means entering and exiting nested world, is also very different from the traditional normal virtualization, right? So whenever guest hypervisor wants to enter the nested world, when it tries to run a VM inside it, right? So at the time there will be a nested entry happening, and this will happen by guest hypervisor executing a SRET instruction with SPV bit set in the SS. So this SRET instruction will be trapped by the host hypervisor, and host hypervisor will do a nested, which we explained previously, and then it will change the nested state to on, and then it will start executing nested world code. And then once there is a trap or IRQ or SBI code, it will again exit and directly first reach host hypervisor, and host hypervisor will try to process the trap, interrupt, SBI call itself if it wants to, or otherwise it will just directly forward the trap or interrupt to the guest world, and the guest world will see a nested exit actually. The one interesting thing is that this whole thing entering the nested mode depends on trapping SRET, And if we trap each and every SRET instruction for guest and nested world both, then it can have a big performance impact. So to cater this thing, what we do is we do a lazy trapping of SRET instruction, and we trap only when it is a running guest world with H status SPV bit set. And whenever the S status SPV bit is cleared, we stop trapping the SRET. So this removes that performance impact due to SRET trapping. So injecting virtual interrupts is also a little different actually. So in that, basically, whenever a guest hypervisor wants to inject an interrupt to the nested world, it will simply set the HVIP bits, which are trapped and emulated by the host hypervisor. And whenever the guest hypervisor does a VM entry or nested entry, it will trap. It will take a host hypervisor will do a nested switch, and at the time of doing nested switch, it will see that the VS IP and VSI bit were non-zero, so it will inject an virtual interrupt, and the guest and the nested world will immediately take an interrupt when it starts running, right? So yeah. So guest page fault handling is one of the most crucial parts of nested virtualization, right? So whenever we are running the nested world, the vCPU is in nested mode, and it is using shadow G stage. And once, since it is using a shadow G stage or a GATP, to fill the entries, the host hypervisor will need to do a page table walk of the guest GATP. So while doing the guest walk of the guest G stage, actually, it might happen that the page is already there and already with right permission. So host hypervisor will simply pick that page, modify the translation directly to a nested peer to host peer translation, and the modified entry is programmed in the shadow G stage, and then it will resume the execution, and then things flow on actually. The one interesting thing is for handling any kind of guest page fault, a host hypervisor will always have to do a G stage walk, right, or walk the guest at GATP. So this can slow down things, right? So to tackle this thing, there are a couple of optimizations any hypervisor can do, host hypervisor can do. Is one is host hypervisor can restrict the MME mode visible to the guest G stage to 3-level page table, or that is SV39X4. Or the guest hypervisor can also create huge pages in the G stage that it creates for the host hypervisor, right? So both things can help a lot actually. And the same thing continuing actually the guest person. So while handling the guest page fault, it might happen that the host hypervisor does not find a page in the guest HTTP, or the permissions of the page are not matching the access. So in that case, the trap has to be redirected to the guest hypervisor so that guest hypervisor can update the guest GATP. So it will do a nested switch and enter the guest hypervisor, and the guest hypervisor will see a nested exit. It will handle the page fault, and if it is modifying a PT, it will also do a HFence, right? So whenever there is a HFence, it will be trap and emulated by HFence from host guest hypervisor, trap and emulated by host hypervisor. So HFence typically shoots down or removes an entry from shadow HTTP, and then once that is done, and it moves forward and does a nested entry, and it will start resuming the nested code actually. Finally, another important aspect of nested virtualization is nested recursion, and it essentially means that guest hypervisor will also try to emulate H extension for the nested world, and so on and so forth, which means we can go beyond L2. We can also have L3, L4, and so on. So anyways, so to achieve that thing, actually, whenever the nested world accesses H extension features, like H extension CSR or the HFence or HSV instructions, or does an SBI call, the host hypervisor will take the trap, and it will redirect these traps to the guest hypervisor, so that guest hypervisor can get a chance to emulate this H extension functionality for the nested world. And like I said previously, in nested virtualization, the host hypervisor or the L0 hypervisor only emulates H extension for the guest hypervisor. So L0 only emulates H extension for L1, and similarly L1 can emulate H extension for L2 actually, right? So, and this is how the recursion will go on actually, right? So moving on to the last part of our session or talk. So there is the software status and demo actually. So yeah, so we do have a complete proof of concept implementation on QEMU for nested virtualization. where in the host world we have XYZ running, in the guest world we have KVM RISC-V running, and in the nested world we have a regular Linux kernel running. And the required patches and software support has already been upstreamed in QEMU and XYZ. And then we do have a lot of work in progress stuff as well. Like we are still working on the KVM nested virtualization support, which means the ability to run KVM inside KVM or some other hypervisor like XYZ inside KVM, the reverse thing. And in addition, we are also working on performance optimization things, like we are thinking of proposing an SBI nested acceleration extension, which will allow host hypervisor and guest hyper to collaboratively accelerate the nested virtualization performance by using a shared memory, which to minimize traps, and also implement the same proposal in XYZ and KVM as well, right? So now we have a time. It's time for a live demo. So I'll quickly switch my screen. So so as you can see, so what we'll do is we'll show a full-blown nested virtualization running. So over here, what first I'll do is first run VM, first run XYZ actually. So as you can see, the command actually highlighted in the bottom actually. So we are launching a Vert machine, and we are going to run XYZ inside it as a kernel, and the BIOS will be OpenSBI, of course, and it will have 4 CPUs. And so we'll see that after booting, it will immediately create a simple 2 vCPU VM, right? So there are 2 vCPUs, and what we'll do is since we are going to run a hypervisor inside the VM, we'll attach attach the same XYZ disk to the VM as well, so that VM can load images for the guest as well. And at the same time, we'll also start the VM. So that's what so the VM is started. It immediately starts the basic firmware of XYZ. So now the guest hypervisor is booting actually, which is the guest kernel inside the VM of XYZ. Okay. So now we have to initialize KVM. Okay. So what we'll do is we'll mount the disk which is used by XYZ so that we can reuse the same images, Linux images. So that's what we have done. And then we'll also insert the KVM module, and we also untarred the KVM tool image, which we'll use to create the VM, right? So, and now we'll launch the VM. So as you can see, we are creating a VM now inside another VM, which basically we are going to create a KVM VM inside XYZ VM, and it will be a single core VM for simplicity, of course. And yeah. So as you can see, it has started booting. So it is little bit, I mean, quite slow compared to the original guest hypervisor. That's because now there are 3 layers running, 3 different worlds are running. So we are seeing the nested world booting actually. And so nested world is a simple Linux, the guest world is a Linux KVM, and the host world is XYZ. And the whole nested virtualization is right now being the H extension for KVM is being emulated by XYZ, right? So another interesting thing is, like, if you notice, right? So this is running on QEMU. QEMU supports SV57 for both HS mode as well as the regular S stage. But over here, XYZ is enforcing only 3-level page table for the guest hypervisor to minimize the page table walks actually. So it has booted, and we can see that. Yeah, and we are also emulating SSTC for the nested world. So we'll quickly power off. and do the same thing with huge pages. So, and we'll see the visible performance difference. So now we'll create the same VM and give huge pages to the same VM, and you will see the speed up actually it achieves. Yeah, and as you can see that the booting is much more smoother than before, right? Yeah, see, it booted much faster, almost twice or thrice faster. Right? Okay, so I think that's pretty much it about this demo. We'll move back to the slides. So I hope you found this demo quite interesting. That's pretty much it about this demo, and I hope this session was really useful to you. Enjoy the rest of the RISC-V Summit. Yeah. Thanks for attending this session.